All right, hello everyone. We are project number 7. My name is Kayvon Sherrod. And our project is titled Predictive Stability versus Fairness and Stability of Chemical ECG Classifications, which is a multi-run analysis of being learning. All right. So our project, we know that AI is being used in healthcare and it's constantly growing, and doctors are using these AI models to classify things. And the problem with that is that these ECG class, the AI models that specify the ECGs are shown to have unfairness. It has to have 100% accuracy, but the problem is that it's diagnosing certain demographics and it's leading to misdiagnosis, which is wrong diagnosis and possibly can harm the patient with conditions. And our research, we saw that when we did multiple runs, that the fairness of these models range from 31 to 47. The part of the problem is because healthcare should be equal for everyone, and it's causing a problem where it's not fair. So in our objectives, we are comparing our 1B CNN versus a hybrid CNN, as well as granting the fairness across the age and demographic, as well as testing the fairness across multiple runs.
AI is becoming increasingly important in the healthcare to analyze the electrocardiograms and help the doctors to diagnose the disease. AI models are evaluated based on how accurate they are, but accuracy is just one part of building a reliable AI models. It is equally important to ensure that it is fair and consistent for all the patients, regardless of their demographic groups. And this is what led to our research question. Is the fairness result from a single run actually be trusted? Because deep learning models, they involve randomness, meaning even if we use a single data and setting, different runs can produce slightly different results. If the fairness changes from one run to another, then trusting a single fairness score may not tell the whole story. That is when to investigate, we use 5 PCG diagnostic classes and 4 demographic groups based on their age and sex. Instead of training the model once, we train the model 3 times using different random seeds and to evaluate the fairness. We also explored 2 additional questions. Can the demographic re-weighting improve the fairness without reducing the predictive performance? And can the transformer CNN model produce fairer results than the baseline 1D CNN? So the overall goal is not just the accuracy, but also to determine whether the fairness evaluations themselves are reliable, because in healthcare, a single result may not be reliable and is not sufficient. Okay, so before starting our project, we did a few prior studies and looked at what we have accomplished. So the first area, it focuses on improving the ECG deep learning model. So in 2012, a study showed that AI models would analyze the ECG and the performance was comparable to the cardiologist. In 2020, Wagner and colleagues, they introduced PTB Excel dataset, which is one of the largest publicly available datasets and the one that we use for our project. In 2021, a study introduced the benchmark splits for PTB Excel, which allowed the researchers to compare different deep learning models and produce comparable and reproducible results. Then the second area, it focuses on improving the fairness. So in 2012, a study introduced demographic reweighting to reduce the biases in machine learning. In 2021, a study showed that even if a model is 100% accurate, it would still be unfair to certain demographic people and could increase the false negative rates. Then in later 2022, a study showed that fairness in PCG is an open challenge. So this is where our study fits in. Instead of only looking at the accuracy, we are making sure that it is fair and consistent across multiple training runs, and while comparing the hybrid CNN model and the baseline one CNN.
But when we did our prior research, we found that prior research focused on more of the accuracy rather than the fairness. as well as they only use a single run evaluation, so they only ran the model one time and got their data from that, as well as they didn't combine like one DCN or demographics, and as well as the reliability. So that's where our research comes in, as we're addressing these research gaps by not focusing on accuracy, but the fairness overall, as well as showing for some demographic groups. So we're going by age and age and demographic, as well as we're doing a combined model where we're comparing to the multiple validations, the fairness and reliability, and we're doing it around multiple times to get our results.
So our research uses a large data set that is the XBXL data set. It contains over 21,000 top-lead BCG recordings. So because some patients will have more than one diagnosis, this is a multi-level classification problem involving 5 diagnostic classes. So our goal is not only to evaluate the performance metrics, but also to evaluate how fair the model perform across different geographic groups. And how do we do this? So we basically compare the three models that we have. That is the baseline one, the CNN model, the integrated model, and also the hybrid CNN model. So our workflow, we began by installing the libraries we use and also loading the PTBXL data set into Google Colab. And also we pre-process the data, that is we standardize the ECG signals, and also divided the training, validation, and also the test sets using the official PTB Excel codes. And then trained our model, that is the one big CNN model and the hybrid CNN transformer. And then we performed a fairness evaluation. Then we did our intersectional fairness to see the false negative rate across the data set. And also we did a fairness certification. So we basically have we basically purchased an inverse people who we went to we trained the model, and then we did the explainability guys to see where the AI made its predictions, and then we ran the project to do 3 rounds. And after that, and also because each of the data set contains 12 that is basically showing different views, different electric views of the heart. So this is also a multi-label classification problem. So our baseline model was a one-dimensional convolutional neural network. May ask, what does that mean? That basically is a baseline model that basically learns local pattern from using the convolutionary blocks or layers to basically make predictions for data fairness in the products. And then our more advanced model is the hybrid CNN transformer. So it basically uses the convolutional neural network to extract the ECG picture the signals, and then it uses the sequence length and also captures a long range dependence. So our project uses the official of child benchmark split. That is about 80% of our ECG recordings being used for testing the model, 10% of the ECG recordings being used for validation during training, and then the last 10% is going to go in for models to be used for testing later on. This is consistent with past research that is done with the same data set, and it prevents data leaks from happening. Our project is using Python or Google Colab as one of the libraries that we include PyTorch, which we use to design and train our different models. NumPy and Pandas, which is used for data processing and analysis. Scikit-learn, which provides us with our evaluation metrics. WFDB, which loads our ECG waveform from PTBXL, and then Matplotlib, which is basically to visualize our evaluation and fairness results. So to evaluate our models, some of the metrics are obviously accuracy, which is just how well our model is able to predict diagnosis for patients overall. Precision, which is how well our model is able to predict positive, make positive predictions, and then recall,
which is how our model is able to actually detect patients who actually have a condition. And then because there is kind of a trade-off between condition and recall, we also include the F1 score, which gives us a more balanced measurement of the two. And then to measure our accuracy, we mainly looked at the area under the RC curve, which allows us to look at measurements using multiple thresholds rather than just a single cutoff value. And then for our fairness metrics, we mainly look at our false negative rate, which essentially is the rate of misdiagnosis. So right away, here, look at our bar graph. We can easily point out some of our results that we found. One being that the dark blue representing our hybrid transformer model was the highest performing model overall. It has the lowest false negative rate across all demographic groups. The second thing you may notice is that among the different demographic groups, our young females are the highest misdiagnosed, and the specific conditions of autosomal infraction, changes in the SDNT region, and reduction disturbance. Something else that we noticed was that our young male patients had the highest false negative rate in hypertrophy at around 80%. But overall, our evaluation performance for our model had an average around 89.5% accuracy, and our F1 score was 66.5%. Which is a pretty reasonable balance between our precision and recall. So as stated before, this is a multi-run analysis. So we wanted to, in order to evaluate how stable our models are, we had to make multiple run-throughs on different randomized feeds. So we retrained and tested the data multiple times on these different feeds. And look at our graph, you can see that our performance evaluation accuracy is pretty consistent overall for the run at around 89%. So there was a little variability between the runs. However, for our fairness metric, it was very unstable, ranging from 31% to 47% between each run. So essentially what this means is that evaluating the model accuracy by itself is not enough to actually evaluate AI clinical systems. Just because a model may be accurate overall does not mean that it is accurate for every person. And in healthcare, you want to make sure that everybody receives fair treatment. And so that leads us to our most important insight, in which predictive stability does not automatically guarantee fairness stability. And then some of the unexpected findings that actually found was the pool I mentioned, the younger males having the highest false negative rate for hypertrophy. We sort of expected to see more of a consistent group being having the highest misdiagnosed across all conditions. So it was interesting to see that it switched from younger females to male for that specific case. So maybe that is something that we want to go into, or it could just be some kind of error. But in comparison with prior research, our results reinforce that it is important to also look at fairness evaluation and not just traditional performance metrics. We want to make sure that we have something fair for everyone and not just accurate overall.
So our general behavior, it basically just contains the ECG inputs, processing, outputs, and all. This is not user interface. Predictive performance versus fairness and stability in clinical ECG design. High accuracy ECG AI isn't enough, but it isn't reliable for every patient. In this demo, we'll show how a framework evaluates fairness, explainability, robustness, and stability alongside predictive performance. Here's how our system works. A patient's 12-week ECG is analyzed by an AI model called clinical research. In this setting, the most critical error is a false negative, a misdiagnosis that can delay life-saving. Using the PTE Excel dataset, we evaluated three deep learning models through an intersectional pipeline, measuring performance, fairness across given set, explainability with VARCAM, robustness, and consistency across three independent nodes. Overall, the hybrid CNN transformer achieved a remarkable ROC of 0.895 and a macroeconomic score of 0.665. But the overall performance doesn't guarantee equitable performance across all patients. For myocardial infarction, diagnostic miss rate vary across demographics, with young female patients experiencing the highest false negative rate. A likely wide subgroup pattern must be evaluated alongside overall accuracy. LATCAM revealed that the model often relied on QRS beats rather than key SE segment features for myocardial infarction, instead of select persistent patterns for hypertrophy. Finally, although overall accuracy remains stable across training runs, fairness measures vary considerably, showing that single run evaluations can overlook important safety risks. Our results show that trustworthy clinical AI requires intersectional fairness evaluation, multi-seat validation, and robustness testing before deployment. Together, these steps help build more reliable and equitable AI for healthcare. Thank you.
So first, these 9 states have several challenges. One of the challenges is the data set preparation. We use the CCG Excel, which contains a lot of patients. And what that means is before we can start actually analyzing that, we have to organize the file, pre-process it, which takes a lot of time. So it delayed our start time of actually analyzing and getting results. Our second challenge was the long training time. Due to the fact that it was a large data set, we had to run it. It took a very, very long time to get our results, which caused it to have a time due to the fact that we only had 9 weeks to present this information to you guys. So, and also, it took a long time because we was running not one time, but multiple times.
So for our innovation, we only used three random seeds to train our data. So if that was enough for us to observe the fairness variability, but if we had used more, then it could provide a stronger measure of stability. Second, we only varied the random initialization. So other factors like hyperparameters, data sampling would also influence the fairness, so it should be explored in the future work. And third, we only use one fairness mitigation method, one decision threshold, and one synthetic noise. So using more approaches would make our study even stronger. Finally, the PTB Excel dataset that we've used comes from a single German population, and it does not include race or ethnicity. So we evaluated our fairness based on age and sex. So it is not generalized to all the populations. Also, it is publicly available and it is not fully identified. So the fairness was measured on age and sex. So the so we did not use the input to train the data.
Okay, for our key conclusion, so aggregate score is stable across C. That means the overall performance metrics were across the training runs were consistent. However, for specific groups, it was inconsistent. And also, a single run fairness cannot be trustworthy because of the time span we had and everything. We only ran the project for this specific amount of time, and it wasn't I would advise that for future reference we should use a bit longer time to make it more reliable. And also accuracy alone is insufficient. So that was one of the key conclusions we found. So we need both accuracy, fairness, and robustness to get like an actual trustworthy clinical AI. And also for future works, we propose to increase the training runs to like 10 to 30 instead of 3 and 1 and also to evaluate it on a more larger data set, and also to advise for researchers to go more deeper into how the AI was able to make its predictions, and also validating it on an independent external data set that includes race for race metadata for more generalization.
All right, so now we want to first thank the distinguished collective, thank you, Dr. Maraki, for providing the opportunity for it. We also want to thank Dr. my group, Elijah, Dr. Blakely, which are a professor, as well as Sudip, which is my graduate school. But the instructions and the mentorship allow us to present this research to you guys. We also get our research team, we're working together over the summer or having a special focus with it. All right, so there's about 4 minutes per question from the audience. What's the difference? You guys, they based on how
So there isn't really a difference between the baseline module and the mitigated module architecture. So basically they're the same. But however, like the only difference is in the training part. So basically we use an inverse frequency gradient modules. So that basically focus on the underrepresented group that we found in after the first training one. So this was mainly so that the model could focus more on those underrepresented and make sure this happen there first. On the CNN part one, we mentioned a neural heart rate. What do we know that? Our neural network. So basically, a neural network is a type of machine learning. So basically, the set of computer algorithms that basically teaches the machine how to predict patterns. And not sorry, not how to predict patterns, but how to learn patterns from the data.
Said, you guys talked about like training it for a longer period of time. That training process, are you like talking about like how many talks you read or like what specific?
Yeah, we're talking about the epoch. So for this project, we use just 10 epochs to train the model. However, we suggest using more epochs because initially we wanted to use 60 epochs. But however, training when during the training it took a very long time. Like we have to leave it overnight for it to finish loading. So for this project, we focus on 10 because of the project time span. But however, for future research, we will propose using a longer one or more trainings and yes.
And how long was the training process for training?
It took actually maybe like 40 to 1 hour, but compared to 60, it took like the whole night and we were still
Based on the prior research that you ran, are there any more promising models that could have less false negatives?
So, yes, our, as we were doing the book with us using the red key box, we were focusing less on like just trying to get overall accuracy and more on like decreasing the amount of misdiagnosis for specific groups so that it would be more even across all demographic groups. So our focus wasn't necessarily on like being the most accurate overall, because there are other models that are more accurate than the model that we built, but we were focusing on decreasing the like amount of upright.
Yeah, time for one more question. How would you include project on the progression?
So as between as Stephanie was saying, we would likely look at more like mitigation techniques, and then also doing more runs instead of just three, so that we can analyze the randomness between all the different keys.
Thanks so much. Right, so now we're gonna take a brief intermission, get our stretch your legs, things like that. And I will ask that